Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2018 Unit 2, Paper 2, and we will be working on question 4. So it reads, butene C4H8 is an organic compound used in the manufacture of commercial solvents, such as the alcohol 2-butanol. Draw and state the name of the displayed formulae of 3 isomers of butene and include a pair of geometric isomers. Okay, so we know based on the formula that butene is an alkene. And so we're going to go ahead and just draw that alkene here. So here it is. So here is butene. I'm going to draw but1ene where I'm putting my double bond on the first carbon. So this is but1ene that I'm drawing. All right, so there we are. A hydrogen here, one here, one here, one here, one here, and then finally one here. And so because I placed a double bond at the first carbon, that one is called but1ene, okay? All right, so that's my first isomer, and I just named it. Now they want us to include a pair, so that's 2 that's taken up as geometric isomers, right? And so for that one, I'm going to move my double bond onto the second carbon, okay? So I'm going to do that one, so let's do that. So now I have C, double bond, C, single bond, C, double bond, C, single bond, C. All right, so now here's what I'm going to have. I'm going to have that on this carbon, I have this methyl group hanging off, and then a hydrogen. And then on this carbon, I'm going to have what? I'm going to have this methyl portion hanging off of this one. So I'm going to have a H, and a H, and then also another H, okay? So that now, I just drew but2ene, but I'm gonna, because I want it to be in geometric isomers form, I'm gonna show you how to then rearrange them to show the 2 geometric forms. So here we are with the double bond, right? If I have a methyl group, so this is the carbon that we're focusing on, these 2, right? So if I have, I'm gonna put my hydrogen here. So that's this one here, and then I'm gonna put my methyl down here. Okay, I'm just fixing up the arrangement here. And then here now I can put this H. So I'm going to put this methyl actually up top here. And then put the other, this H downwards like I drawn it there. And so when you look at this, you see that the methyls are on opposite sides, right? They're just like transverse. And so that would be trans but2ene, because again, my double bond is on the second carbon, right? So that's trans but2ene. And so if I'm counting like this, where this is my carbon 1, and that's my carbon 2, that's my carbon 3, and that's my carbon 4, right? You see that that's trans because they're on opposite sides, and then but because there are 4 carbons in all, and then 2ene because the double bond comes from my second carbon. So that's my trans, where they're transverse to each other, these substituents, the methyl substituents. So then I can also draw the cis version of this, where the CH3 and the CH3 are on the same side, and that is a possible molecule because of the restricted rotation about the carbon-carbon double bond. So if I were to draw that one, I'm gonna just bring that one, let's bring that one here. I'm gonna bring it here. So C double bond, C, right? And now I'm gonna have both methyls on the same side. So that one is gonna also go here. And then CH, no, I have an H here because I put them on both sides, the same side. right? And so now you see that they're both on that same side of the carbon-carbon double bond. So we're looking where the substituents are in relation to the carbon-carbon double bond. They're on both sides. They're both on the same side of the carbon-carbon double bond. And so again, number the carbons, carbon 1, carbon 2, carbon 3, and carbon 4. And so because my double bond is on the second carbon, it's going to be a butene again. It's the same thing. Same last part of the name, butene. But no, because they're on the same side, the methyls are on the same side of the double bond, I say it is now cis. Okay? And so these two together constitute now our pair of geometric isomers that we were supposed to include in our answer here, okay? So that's my pair of geometric isomers. Okay, so now we've shown our 3 isomers and we've named them and we've also drawn them. And so with that, let's keep it moving. All right, so let's clear this and we're going to move on to part 2. Part 2 says we're supposed to draw the displayed formula of 2-butanol. So that's an alcohol now with the OH group being on the second carbon. And it has 4 carbons in that backbone. So here's what we're going to draw for that now. 1, 2, 3, 4. So I know that from the name but that I needed 4. I know that from the 2, I know that in the 2 positions on my second carbon, I need to have my OH. Okay, so I'm just going to drop my OH there and then just fill out everything else with hydrogens. And so here we are. Hydrogen here, a hydrogen here, a hydrogen here, here, and then finally one here. And so this is 2-butanol, okay? That's all that we need to do there. And then now let's see what else is being asked of us. So for part 3, we're being asked to state with one reason, just give me one reason about the type of isomerism that 2-butanol is expected to exhibit. Okay, and so we're going to come back up here and we're going to look at our 2-butanol displayed formula that we drew. Okay, when I take a close look at my 2-butanol, what I'm realizing is that there is a chiral carbon. So this carbon right here, it turns out that it has 4 different groups attached to it. So let's count. Here's one group that's attached to that carbon, and this is my ethyl group. So you see that that's a C2H5 group right there. So that's one group. Here's another group. This is my OH, right, which we know is a functional group here. So that's another group. And then when I come over here, I see that I have a methyl group. So I'm just gonna circle that one around. That's my methyl group. So that's my CH3. And then I see that I just have a little hydrogen hanging out up here. So I see that I do in fact have 4 different groups. So let's just jot that down real quick. I'm gonna put the reasoning down here. All right. So what is our reasoning then? We are saying that there are 4 different groups attached to one of the carbons in 2-butanol. So it is a chiral. It's what we call a chiral carbon because it has 4 different groups attached to it. Okay, so let's keep that in mind. So when we have a chiral carbon, we have chiral carbons give rise to what we call optical isomerism. Okay, so we're gonna have a pair of optical isomers. We'll get a pair of optical isomers. Optical isomers, and here's the interesting thing about them. They are superimposable mirror images of each other called enantiomers. Okay, so let's just kind of break it down. I'm gonna draw it just to make this super clear to you, but this is literally what you would write. That's your reasoning. You see that there are 4 different groups. And so there's a chiral carbon here, and so that gives rise to optical isomerism. We get a pair of optical isomers. They're non-superimposable mirror images of each other, and they're called enantiomers. So let's just kind of sketch that out real quick so that you have that basis and you've seen it done here, even though it wasn't required for this question. We're gonna go ahead and just show you what that mirror image and that chiral carbon, that whole thing, what that looks like, okay? So here's my chiral carbon. I'm gonna draw my chiral carbon back, and I'm just gonna put a star beside it again. And the 4 groups that we said were around it, we had a methyl group. So I'm gonna go ahead and just draw my methyl pointing up here. We have a hydrogen group, so I'm gonna put my hydrogen on a dash here. I'm gonna put my OH on a wedge pointing this direction. So that's my OH, and then my ethyl, this one, the 4th group, I'm gonna put this way. Okay, so that's my ether, which I'm just gonna break it up as CH3, CH2, same thing, C2H5. Okay, so what we're saying is that this is a chiral carbon, 5 different groups around it. There can be a non-superimposable mirror image of it. So if I put a mirror here, M-I-R-R-O-R, if I put a mirror here, then I'm gonna still have my chiral carbon, but the hydrogen now, which was previously on the right, is gonna be going now towards the left. Right, just as when you look in a mirror, how things are inverted, right? And then the CH3 now, everything that was on the left will become on the right, and things on the right will go on the left now. So my OH that was previously pointing towards this direction, towards the right, will now point to the left, right? And my H that was on the right will now be on the left. So that's what I got there. And then here, again, this was on the left. Now it will be on the right. And I'll have CH2 now coming in, and then the CH3. And so there we go, right? Those are non-superimposable mirror images. And if you try to put them on each other, good luck. They're never gonna impose on each other, superimpose on each other, right? They're actually 2 different molecules, but they are optical isomers of each other, known as enantiomers, a pair of enantiomers. Okay, we could say a lot more about them, but we'll just stop here for now. So that's what would happen there for 2-butanol. Okay, optical isomerism. So this is our big keyword here. Optical isomerism is a type of isomerism here. So let me just box that word. This is our big keyword here, optical isomerism, and that's due to the chiral carbon. Okay? All right, so with that, let's move on to the other question. Definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right here, you'll find our Module 1 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.